Welcome back, class. Thanks for tuning in. Again, kind of what we've been working on the last couple, days or weeks, I guess, is integration. It's kind of our first priority. But again, these are just voluntary. Thank you for those who are participating, and this will hopefully help your transition into college for next year. But again, this is second and long distance from the first priority, which is take care of each other, stay healthy, stay safe. That's always got to be the priority right now. But let's kind of jump into the iPad here and kind of look at what we're going to be doing. We're going to be doing for today. Obviously, we're going to be we're in week 3 here, week 5, part 3, which is antiderivatives still, but we're doing integration by substitution. And so that was on the Google form. Now the Google form had quite a few problems on it. I think there was 10 problems I picked out, kind of a range. Again, you didn't have to do them all. There were some that were kind of tricky. I just kind of threw them at you to see kind of what you could do. If you tried them out, great. If you didn't, that's fine. I just wanted to hopefully give you a chance to see some kind of new material, but also mix it with some of the old stuff. So there is some things we could do here. So, but let's jump right in here and let's kind of go through each problem. Some of these are kind of tricky, and again, Sorry, it was just one of those things. I just want to see what you guys could do, and you guys obviously get to see them right now. So let's kind of jump right in. Okay, so what we're looking at here first is a problem where we have to do a substitution, right? The trick was, what I always told you, is to substitute the thing in the parenthesis out. That's what we want to look at. So what we're going to do here is we're going to make my w the 3x plus 1. That's kind of the idea, what I want to do here. Now, by making that my w, that means the derivative of that, the dw, if I took the derivative of both sides with respect to both variables, so the derivative of w is 1 dw. The derivative of the right side here would be 3 dx. And now, why that's important is because both of these items are going to be found if I do an actual substitution step. Now the problem is the 3 isn't apparent. Why this isn't apparent is because of this 12 here. This 12 is actually 4 times 3. Now why that's important, this is 4 times 3, is because the 3 and the dx are this thing. And the w is going to be this part. And so the 4 is the thing I can't account for. So when we actually do this problem, this is what we're going to have. If there's a constant out front, you can kick it out of the integral. And so what we're going to be having here is we're going to have this. We're going to have a w to the 3rd power, because I'm substituting out the 3x plus 1 as w. And then the dw is going to represent my 3 and the dx. This will be the dw. That accounts for everything, including the 12, because the 4 and the 3 were the parts. So the 4 was kicked out, the 3 and the dx was the dw that I substituted in. So now this is just a power rule. So if we just do a normal power rule for an antiderivative, you add 1 to the power and you divide by the power. That's a normal antiderivative. Now we still have the 4 out front, because if you do an antiderivative, the constants out front stay there. And so what happens here is that when you multiply, these 4's cancel. That's it's a normal cancellation rule for fractions. And so what we're left with is just a w to the 4th. That is the antiderivative. Now the problem is we didn't start with w's, right? We had x's in the original problem. So I have to just substitute what we took out earlier for w. My w was a 3x plus 1. So I'm substituting that back in, and this is the answer I'm looking for. That's the antiderivative. Now, I know there's the plus c in the back, the constant, the plus c, because there could be any number in the back when you do an antiderivative, but this is the answer. That's the antiderivative for this problem. That's by doing it by substitution. It makes it a lot easier to do, and it's quicker because you can just do quick substitutions. All right, let's jump right to the next one. Now we're getting to the tricky ones. Now we have trig functions kind of everywhere, and it's going to rely on whether you remember what parts we have to do. So, so on this particular problem, I'm going to switch up the color here. So on this one, I'm going to use my w as tangent. Now I know that isn't apparent. Like, why would you pick that one? Is because I know what the derivative of tangent is, right? If you think back to all the derivatives we've taken, the derivative of both sides, the derivative of tangent would be secant squared dx. That's the derivative of tangent. That's where you can start to see where this is coming in. The only thing I can't account for is the 2, and it is a constant, so we can kick it out front. So what we have here is we have a w for the tangent, that's this part. We have the dx, or sorry, the dw, which will represent this and this part. So that'll be the dw, that's the secant squared x dx. And so this is the antiderivative, so I'm just doing it for w, sorry for notifications. So the w, the antiderivative of that is w to the second power over 2. It's a normal power rule. We still have the constant out front that we're going to multiply by, and we have the plus c in the back, right? The 2's here's cancel because when you multiply, they would cancel each other out. They're reciprocals of each other. And I'm left with w squared. Oh, weird, it's not letting me write that 2. This is so weird why it doesn't let me do that. There we go. Weird. Okay. Plus c. Okay, so we've effectively simplified this. Now the last thing I have to do is substitute what w was. W was a tangent. So what I have here is a tangent squared x plus c. And that is my final antiderivative. And again, why it was squared? Because that was the w squared. So it's tangent squared. So there you go. And that's my final answer. That's the antiderivative. All right, let's move on to the next one here. All right, so this one, this by far is the toughest problem out of all 10 that I provided you. And apologies, I really didn't give you any rules for this one. The trick is on this one, and it's quite the trick, sorry, is to do this. Is to start by doing this. All right, so it's to know, sorry, let me rewrite that. It's to know this simple property. This is something we talked about in pre-calc. It is called a Pythagorean identity. It is used for doing trig identities where you do substitutions with them. And so what I'm going to do is I'm going to rearrange a little bit. I know it's not apparent why you should do this, but I'll explain here in a second. Okay, so I'm solving one side. I'm solving for cosine. And why this is going to be helpful is because I'm going to do a little bit of substitutions by normal like trig identity rules before I attempt to take the antiderivative of this problem. So cosine squared represents 1 minus sine squared. That's a normal rule for Pythagorean identities, right? Something we did back in pre-calc days. I'm going to substitute that in here. So what I mean by that is that this is the original problem. This is the same problem just written differently before I even start. It's cosine of x times cosine squared of x dx. This is still the same problem because when you multiply a cosine by cosine squared, you get cosine to the third power. You add them. The bases are the same. You would add the powers together. This is where you start to see it. I'm going to substitute this in here. Why? Is because it will make this problem easier to take the antiderivative of it. Because it's the way when you do substitutions and you take derivatives of substitutions, you have to account for every term, right? The derivative of cosine would be sine, and there's no sine on this problem, not yet. So that's why you can't just substitute cosine out and say it's w, and w to the third power is because I don't have a sine left over. There's no sine on that problem. I will make it there by doing this simple rule. So here's what I'm doing. I'm substituting the 1 minus sine squared in for cosine squared, as you can see with my little arrows. I'm going to go back to red here. And this is actually the same problem. It's cosine of x times, in parentheses, 1 minus sine squared of x dx. This is still the same problem. I haven't even started taking the antiderivative. I haven't even done my real like w substitution stuff yet. I'm just rewriting the problem in different formats so that it's possible to take the antiderivative of it. Now what I'm going to do is I'm actually going to distribute this through. I technically don't have to, but I'm going to. It's just, to me, it's easier for me to see and maybe to explain it to you. So I'm going to multiply the cosine through. I'm going to like distribute it in like that. All right, so here's what we have. We have cosine of x. Oops, don't need a d. I need a minus sign. Cosine of x times sine squared x dx. This is the entire the entire integral. Sorry. This is the problem that I'm going to be doing. This is the form. This problem, what I have written here in red, is the same as the original problem. It's just written differently. I know that's not apparent to do that. It's one of those things that when you do enough integrals, you can start to see shortcuts. You can, there's different ways of doing problems, especially like derivatives. There's different methods of doing derivatives. There's different methods of doing integration, and this is one of them. It's using identities. And this is something we didn't really discuss a lot in pre-calc. I just said it was important because this is where you're starting to see it. So this is the problem I'm going to be doing the antiderivative of. Now I'm going to erase all this other work that I have here in front of me. Apologies. But this will lead me to the actual substitution rules we have. So I haven't even started the problem yet. Sorry. This is the hardest problem out of all. So I'm going to erase all the stuff we have except for this problem that I have written on the bottom. This. Because that's the problem that I'm actually going to be doing my normal rules on. Alright, so this is an integration of x minus cosine of x times sine squared x dx. Alright, that's a square. Okay, now I can get rid of this stuff. Okay, now we can start the problem. We have a minus sign in the middle, so this, when you do integration, you can separate them by the plus minus sign. That's a rule of sum and difference. So again, I'm going to switch up my color here. So this is the same problem. You can do that for sum and difference. You can't do it for multiplying. So that's why you do it this way. The reason why is the antiderivative cosine is antiderivative of cosine is sine of x. That's the normal antiderivative for sine. Because if I take the derivative of sine, it would get me back to the original problem. So there's that problem. That's the first answer. In the back here, this is where I'm going to start doing substitutions. I know that's weird. I'm going to use my sine as my w. So sine will be w, and I'll put this I'm going to write this off a second. Maybe I'll do a different color here. Alright, yeah, let's switch this up. Alright, so I'm going to say that my w is going to be the sine of x. Okay? Hopefully this makes sense. So w is the sine of x. That means dw is going to be cosine of x dx. I can have everything accounted for here. Because I have a cosine in here, it's right there. I have a sine, which is actually squared. You'll see that here in a minute. And then I have the dx. Everything is accounted for. So when I start substituting on this back part, it makes it easier to see why I'm doing this. Alright, so here's what we have. We have the integral. I'm going to plug in my w, so this will be w squared because it's sine squared, so w squared. And then this will be dw. And the dw is representing the cosine and the dx part. So everything is accounted for. So when I do the antiderivative of this, so when I do the antiderivative of w squared, this is w to the third because you add 1 to the power and divide by the power. That's just the normal power rule. And then that's literally the antiderivative. And then I just have to substitute what my w was. So if this is the problem so far, and I have the plus c in the back for all the constants. But substituting what my w was, my w originally was sine. So if I go back and I take out this w and I plug in a sine there, this would be sine to the third power. And this is my answer. That's the full antiderivative of the original problem. If I take the derivative of this thing, it would go right back to the original problem. I know that seems weird. It does work. Okay. Now that we got that problem out of our system, all the rest of the problems, no joke, they're all easier than that last one. Because I don't have to do any weird rules. I just have to do normal substitution stuff. So apologies for the last one. Okay, so let's go through the rest and let's finish this out. So my w on this problem is going to be my sine of x. My dw is going to be the derivative of sine is cosine of x dx. So substituting these in, the only thing I cannot account for is the 5. So that 5 will be kicked out front. So I'm going to write it like this. And this will be w to the 4th power, because that's sine to the 4th. And then the dw is going to represent that cosine of x dx part in the back. So the antiderivative of w to the 4th is w to the 5th, because you add 1 to the power, divide by the power. And that's being multiplied on the 5 out front. So the reciprocals would cancel. I have the constant, right? And now substituting in what w was, it was originally sine. So this is sine to the 5th power plus c. And there's your final problem on that one. That's it. That's the final antiderivative of this whole problem. All right, let's keep going here. Hopefully these are going to get a little bit easier as we go. Let's see. There we go. So on this problem, and this is just kind of a normal rule, I'm going to say that my w is going to be my x to the 3rd. So if we do this problem, so my w is going to be my x to the 3rd here. And so the dw, if I take the derivative of this thing, this will be 3x squared dx. And that is accounted for, right? That 3x squared dx is right there. This would be my w, so everything is accounted for. So it looks like on this particular problem, if I kind of rearrange and I substitute, this is what we have. We have cosine of w dw. That's doing my little substitution rule. The antiderivative of cosine is sine of w plus c. That's the antiderivative of cosine. And then I just substitute in what my w was. My w was x to the 3rd. And there you go. There's my answer. Okay, so hopefully this is starting to make a little more sense. Let's keep moving on here. We've got a few more problems to go here. Got, what, 5 more problems to go? Okay, so again, trying to figure out what to substitute. I'm going to pick the larger item. So my w is going to be my x squared plus 3x. The derivative of that is going to be, so that'll be the dw part. That'll be 2x plus 3 dx. That's the derivative of that. And you can see that part's right here and right there. So that is accounted for. So hopefully this is starting to make a little more sense. So if I do my little substitution here, this will be w squared dw. Because that x squared plus 3x was squared, so that's why it's w squared. And then the dx was the 2x plus 3 dx. So now the antiderivative of this is w to the 3rd over 3 plus c. That's the antiderivative, and now all I have to do is substitute my w back in. X squared plus 3x is to the 3rd power over 3. There we go. Couldn't get that 3 to show up. And there you go. That's the final answer. That's the antiderivative of this original problem. If you take the derivative of this, it'll go right back to the original problem. Let's go to the next one. We only have a few more problems left over. Okay, so on this particular problem, this one's going to be a little trickier. It's nothing special. It's not as hard as that, the one with the cosine to the 3rd. It's just the way that this one's written. It's not apparent what to do. So here's what I'm going to do. I'm going to figure out what my w is. My w is always usually the part in the parentheses, so it's 1 minus the x squared. So if I take the derivative of that, that'll be the derivative of 1 is 0. The derivative of the x squared, negative x squared, is negative 2x dx. Okay, now, it doesn't look like it's apparent. That part is written on the top here. So you can see my little arrow up there. You can see that there's an 8x dx up there. Part of that is represented by this thing. That is part of it. So what I have to think about is, like, how did they get from like this negative 2x to get to this 8x? Well, what they did is 8 is the same thing as negative 4 times negative 2. So I can just substitute those parts in, and now everything's accounted for in this problem from my original problem. So the negative 4 is a constant. It can go out front. The negative 2x dx part, that's accounted for here with my little arrow here. And then the w is going on the bottom to the 4th power. And this part here is going to be my dw. And I'm going to put it in the back. Let me get rid of this. So this is what it's going to look like. The dw is back there. That's the negative 2x dx part, because I want it all to be one variable. So you can start to see how I'm doing this problem. Now, I'm not started yet. I'm going to move this w up. I can't do like a natural log because this is w to the 4th. If it was like 1 over w, I could just do a natural log. That would be the antiderivative. But this one, I'm going to move that w up and make the power negative. So I'm putting on the top of the fraction. So that's in That's the negative exponent rule. Now I can take the antiderivative, because the antiderivative is just normal power rule, right? It's, you know, it's a variable to a power. So you add 1 to the power, divide by the new power. That's the rule. And then you put a plus c on it. So you add 1 to the power. So adding 1 to a negative 4 is negative 3. Divide by what the new power is, and then that constant out front was multiplied on. And so your final answer is that two negative signs are going to cancel out, so I'm going to be left with 4 on the top. The 3 on the bottom is still there because the two negative signs. And the w to the third, I'll just put it on the bottom now. And there you go. This is the final antiderivative. Now, I say final. I should say I need to substitute what w is, because that was something we took out earlier. But that's the antiderivative of this problem. It doesn't look apparent when you first look at it, but that's what it is. And so what we have here is we have a 4. I'm going to plug that w back in. The w was a 1 minus x squared, and this is all to the third power plus c. And there you go. Now that is the final answer. A little bit ahead of myself. Let's move on. We have, what, 3 problems left? 9, 10, 11? Okay, so in this one, just like before, I'm going to say my w is the x to the third. That's kind of the part in the parentheses here. The dw part will be the 3x squared dx, because that's the normal derivative rule. You drop the power up front, subtract 1. And so everything's accounted for except for this 3. This 3 is not accounted for. You can see on the original problem, there is no 3 here. If there was a 3, it'd be nice and easy. So there is no 3. So what I'm going to do is I'm going to divide this 3 over so it looks like this. This part is accounted for, the x squared and the dx part. The 3 will go over to the other side. I'm going to divide the dw by 3. That's the part I'm going to substitute in for this stuff. So hopefully that makes sense to you. So what we have here is e to the w, dw, and the dw part had a 1/3, so I'm going to put the 1/3 out front. That was a 1/3 dw, and it's a constant, so I can throw the 1/3 out front. That accounts for the lack of a 3 on this original problem. The derivative, the antiderivative of e is just e. Right, that's the antiderivative, and now I substitute in what my w was. My w was an x to the third. And there you go. That's my final answer. That's everything accounted for. Let's go on to the next one. Okay, so this particular problem, just like before, I'm going to say my w is going to be my x to the third plus 1. My derivative of this is going to be 3x squared dx. The derivative of 1 is 0. So what I have here on this problem, just like before, you can definitely see this part is in the original problem. It's here and here, but the 3 is not accounted for, so I'm going to divide this 3 over, so it's a 1/3 dw again. All right, and that x squared dx is accounted for. So substituting these back in, here's what we have. We have this. We have a 1/w dw, and then the 1/3 would have been out front because it was a constant. This problem, since it's just 1/w, there is no power on the w, this would just be the natural log of w. That's the antiderivative of 1/w. It's just natural log of w. The 1/3 is still out front, plus c. And then all I have to do is substitute in what my w was. My w was x to the third plus 1. And there you go. There's the original problem. If you take the derivative of natural log, it goes back to 1/x to the third plus 1. And then the derivative inside of that parenthesis. Okay, let's go on to the very last problem here. Well, these are starting to make sense. Looks like on this particular problem, my w is going to be x squared. The derivative of that will be a 2x dx. And that 2x dx is accounted for, so I don't have to do any weird, like divide by 2 over. It was accounted for in the original problem. So it looks like this problem is going to be the antiderivative, or the integral of sine of w dw. The antiderivative of sine is negative cosine of w plus c. That's the antiderivative of sine, because if you take the derivative of cosine, you'd get a negative sign, so negative would make it positive. So you have to remember how the derivatives work. So substituting back in what my w was an x squared. And there you go. There's my answer. Okay, I know that was a lot, especially that third problem that we did, where it was kind of tough with we had to use the Pythagorean identities to do that. Again, thank you for those who are volunteering, to do some of these. If you haven't, maybe take some time over the next couple weeks to try out some more stuff. Again, this is not meant to, stress you out. It's meant to just be an opportunity to continue your education. I know this stuff is really hard. I understand that. Some of you aren't, maybe submitting your Google form answers. It's fine. Maybe you're just trying on a piece of paper. But I try to provide you the answers each week so you can at least see what you're doing. But again, this is all voluntary. It's not as important as your health, as important as taking care of your family, taking care of each other. But again, I miss you guys. I know a lot of you are kind of looking forward to graduation, and that's still kind of being debated in how they're going to do it. But again, if any of you are concerned about your grades or whatnot, just let me know. But again, miss you guys, and hope to see you guys real soon.